All right, welcome to an early morning Simpkins Physics Corner. Yesterday we were working our lab and we collected data for a tennis ball dropping 1 meter. This is what your data might turn out to look like. Now I had a cell phone timer going in the background and my tennis ball started dropping at 2.23 seconds. Now if you started at 0, you can skip this first step I'm about to show you. But the cool thing about LoggerPro, if you notice here, we do our curve fit, and if we try to fit a quadratic, we see that curve that we expect because a falling tennis ball will be experiencing acceleration. But we want to know the relationship between the position and the time. Well, we know that it's quadratic, but we want to try to linearize this function to get a coefficient that relates these two variables together. And so we notice this is a curve, and we know that that has to do with an x squared type of deal. So what I'm going to do first here is get my time a little more simplified. Now, if you ever want to do something with your data, all you have to do is go data, new calculated column. All right, so I'm going to call this one delta time, which means the time change from 0. And I'll just call this one real time. Units will be in seconds. So here's what I'm going to do. I'm going to take my time, and what you do is you click on variables or columns, and it's basically like typing in a formula here. All you have to do is time, right? And I'm going to say minus 2.23. The reason I picked that number is because that's my initial value. And if you think about it, that will start my initial time at 0. If you hit done, you can check it real quick. Look, my initial time was 0, and it would look like the ball was falling for about 0.3 seconds. Okay, so now I can graph my real time versus position. And of course, you notice nothing really changes. We still have a quadratic. But when we seek to linearize a function, what we're going to do is try to pick up a relationship so that this curve is linearized or turn into a straight line. Since we have a relationship right now, position is related to time squared, what we're going to do, and the reason it's time squared is because you can see this x squared curve from the generic formula for a quadratic would be y equals something having to do with x squared. What we're going to do is we're going to add one more data calculated column, and I'm going to call this time squared. Okay, and I'll just shorten that as t caret 2, and we'll call it units of seconds squared. And we're going to go ahead and say delta time, that's our raw time starting from 0, squared. That's all you have to do, caret 2. Done. Now you can check to make sure, just look and see if these look like they are squaring the numbers, and indeed they are. Then you're going to click on your x-axis label down here and change it to time squared. Look what happened. Now that we graphed position versus time squared, it's no longer really a quadratic, right? That doesn't look like a quadratic to me, not at least one is sensible. It's actually a linear function. And this is what's really cool. Look at this slope, 8.58. Now, we did this with a very rudimentary system where we're using a slow motion phone camera with a timer that only displayed every few milliseconds, right? It actually skipped a lot of times. And we got 8.58, which is getting towards 9.8 meters per second squared, which is what we expect our acceleration due to gravity to be. So we know what the real answer is, 9.8, and the closer we get to that, the better. But this is how you linearize. Once you see a relationship between your initial two variables, in this case time and position, whatever that looks like, in this case it was y equals x squared, we're going to go ahead and change our x-axis to reflect the relationship we expect to be linear, in this case position versus time squared. Now we have this coefficient to relate the two together, and we actually are getting close to some real value.